If you take a look at our goal for this section, we're graphing. Again, I told you we're graphing all week. So that is what we are doing again today. You've seen this definition before. It just looks a little scarier. Patients picked out this equation, on day one is a little bit frightening looking. But please bear in mind that all this is saying, real simple, is that the numerator is a polynomial and then your denominator is a polynomial. That's all this is saying. So when you're dealing with a rational function, you have a polynomial on the top and a polynomial on the bottom. What you need to come to understand ultimately is that that bottom, q of x, is never allowed to be 0. And we've seen that a couple times. Ultimately, when that equation ends up being 0, whatever value of x gave us that polynomial to be 0, that was our vertical asymptote in the last section. So that'll happen again today. All right, so here's the breakdown. In the next couple parts underneath this screen shade, what you're going to see is how do you find your intercepts and your asymptotes, because that's what we're going to work on first. So in the last section, all we had to do was find our asymptotes and then our branches. Well, today we're going to find our intercepts, asymptotes, and then sometimes these graphs have branches and sometimes they don't. So you will need a graphing calculator to get through this lesson a little bit today. With that being said, so how do you find the x-intercepts of a graph? And it's pretty simple. All you're going to do is take the numerator, the top polynomial there, and you're going to set it equal to 0 and solve. So whatever that numerator is, you set it equal to 0 and you solve it. That tells you what your x-intercepts are going to be. And if you think about it, that does make sense. Like I said, if this guy here, that's your numerator, the thing on the top. If you take that top function and you let that top function be 0, well, what did you just do to your fraction? The whole thing is then equal to 0. That's the value where y is 0. So it actually does make sense if you give it a little bit of thought. The next pieces that we have to find are surrounding that vertical asymptote. The vertical asymptote can be found by setting the denominator equal to 0 and solving. So in step 1, we set our numerator equal to 0 and solve. In step 2, you set your denominator equal to 0 and solve. This time around, in step 2, when you set your denominator equal to 0 and solve, you end up finding your vertical asymptote, so that's pretty handy. Again, this also makes sense if you set that denominator equal to 0. Essentially, what you're finding is the place where x can't be. So that gives you your vertical asymptote. Okay, now we're going to talk about the horizontal asymptote. We talked about it a little bit yesterday. I said there's 3 cases. So here are your 3 cases. We've done these 2 already. We did the case where the degree of the numerator is less than the degree of the denominator. And automatically, for our original hyperbolas, the asymptote was at 0. So when we did our inverse variation graphs, like y equals a over x, the degree of the numerator was less than the degree of the denominator, so your asymptote was automatically at 0. If the degree of the numerator is the same as the degree of the denominator, you just divide out these numbers in front. They're called your leading coefficients, so they have it as a sub m over b sub m. And then, lastly, if the degree of the numerator is greater than the degree of the denominator, there is no horizontal asymptote. It actually has quite often something called an oblique asymptote. You could take care of that next year. We don't do it here. They're neat looking though. You know what your obliques are? Yeah, muscles in here, right? You like bend them your side. Well, that's what the asymptotes look like. They're like little bends in the graph. They're pretty neat. I just wanted to make sure, did you fix that typo in your notes? It should say a sub m over b sub m, or n, sorry. Okay, one last little note. Horizontal asymptotes don't act the same way vertical asymptotes do. And here's what I mean by that. Vertical asymptotes are just to describe the way the graph behaves at the ends. So they're descriptors of end behavior. They don't have to match the range. Vertical asymptotes, however, right away, that's directly linked to your domain. But the range and the horizontal asymptotes, those can actually be a little bit different. So you're going to see that a couple times today. So there's our punch list of things to do when we go ahead and graph. You find your x-intercepts by setting your numerator equal to 0. You go ahead and find your vertical asymptote by setting your denominator equal to 0. And then you figure out your horizontal asymptote, make a t-chart, you draw your graph. Ready to do it? Giddy up, let's do it. Oh no, give me my attendance folder. Sorry. Thank you. Okay, so let's do this. In example 1, it says graphing a rational function where m is less than n. And when you see that particular notation, they're just talking about the degrees. So if you look here in part A, what I see is that the degree of the numerator, which doesn't even have an x, is less than the degree of the denominator. So there is like a little x attached to the 3. It's like 3x to the power of nothing. But you remember anything raised to the 0th power is 1. So it's safe to say that the degree of the numerator, 0, is less than the degree of the denominator. So that's why this problem falls in this category. The degree of the numerator is less than the degree of the denominator. All right, step 1. You try to set, going back through, your numerator equal to 0 to find any x-intercepts that this curve might have. So if we were trying to think about potential x-intercepts for the curve, we would be setting 3 equal to 0. Can you do that? 3 equal to 0? No. So this graph, not going to have any x-intercepts. No x-intercepts. Next in our punch list, we just found our x-intercepts. Now we're going to go ahead and set our denominator equal to 0 to find the vertical asymptote. So I'm going to take x squared plus 2 and set that equal to 0. Subtract 2 from both sides. Square root both sides. Huh? You're taking the square root of a negative number. Can you have that? Can you take the square root of a negative number and get a real number, like something I could actually graph? What do you think? No. So this doesn't work out, which means it's got no vertical asymptote. Next up, we got to think about our horizontal asymptote. So bullet number 3 there. Again, we're talking about the case in this problem where m is less than n. When the degree of the numerator is less than the degree of the denominator, which is what we have going on right now. Because our degree of our numerator was 0, and the degree of the denominator is 2. Because the degree of the numerator is less than the degree of the denominator, it is safe to say that our horizontal asymptote is going to be at 0. So to kind of summarize a little bit before we make our t-chart and get our graph, the numerator had no zeros, so there were no x-intercepts. The denominator also had no real zeros, so there was no vertical asymptote. Oop. I'll just abbreviate. There's no vertical asymptote. The degree of the numerator, which is 0, is less than the degree of the denominator, which was 2. So the line y equals 0, or the x-axis, is actually our horizontal asymptote. Now to get our t-chart, we're just going to throw this into our calculator and grab some points. So you go ahead and grab your calculator. Don't forget to quantify your numerator and your denominator. Y equals 3 divided by x squared plus 2. Press graph. There you go. You could even zoom in a little bit. Notice today, all of a sudden, it is not a hyperbola. That is a speed bump. That is not the technical term for that graph. I just think it looks like a speed bump. So we now need to go to our table of values to grab a couple points and plot them. So if you go to your table, first of all, I'm going to make sure my table set starts at 0. If you go to your table, you know, you want some negative, some positive. So it might be useful to graph -2, 0.5, -1, 1, 0, 1.5, 1, 1, and then 2, 0.5 for your graphs. So you can go ahead and take a second, plot those points. All right, so yeah, those look awesome. Well done. Last thing we always have to talk about is the domain and the range. Okay, so what is the domain for this particular curve? Possible values of x. Do you know, Brian? All real numbers, yes. Or -infinity to +infinity. In other words, as you're walking along the graph, you know, pretend you're going for a walk. Everywhere you stand on this x-axis, you're going to see a value. So that's very, very good. What about the range? This is tricky. If you get this one, I'll be impressed. Oh, go for it, Kara. Come on. It's not -infinity to +infinity. Perfect. Ooh, you were good with the first part. Yeah, just it starts at 0, but it doesn't touch it, so that's a parentheses. Nice job. And then it goes up to 1.5 and stops. 1.5, close that bracket. So you were good with just the first part of your answer, Kara. Well done. Remember, range is just the space that a graph takes up on the y-axis. So this doesn't go from -infinity to +infinity because there's nothing down here and there's nothing up here. You don't have to write those. That was just, you know, to show you there's no points down there. There's no points above 1.5. Are there questions about that? You ready to try one? See how it goes? Real similar. But really what I want you to focus on, if you're a person who has trouble, you can't remember the steps, you're learning something new, be patient with yourself. Flip back to where we made our list of things that your graph should have. Step 1, we usually try to set the numerator equal to 0 to find the zeros or x-intercepts. Then you set your denominator equal to 0, so on and so forth. So I'll give you a chance to try that one out. So there's my graph from last year. The answer key that I made for last year's problem. But as I walked up and down the rows, that's pretty much what y'all have. So really good job. Really, really good. You know, and just to kind of bullet through the order in which I do the steps, right away, you just, like I said, good habits. You want to keep good habits. Right away, I tried to set the numerator equal to 0, even though I can't set 12 equal to 0. I did it just to show you, hey, that's the first thing you do. You set the numerator equal to 0. You solve. That'll give you any x-intercepts, but there weren't any here. Then I had to set the denominator equal to 0, and then once again, I'm like, oh man, square root of a negative number, I can't plot that. So there was no vertical asymptote as a result. The degree of the numerator was 0, and the degree of the denominator is 2. And because 0 is less than 2, the fun fact you need to remember from our previous lessons is that the asymptote is automatically at 0. And then I made my t-chart, I plotted some points, and there's still something missing. What is missing? It's usually given to you on the test, like they say you have to find it. What do you think, Will? Yeah, so let's have a little talk about that, shall we? Domain and the range. Will, do you know what the domain is? Good man. And anybody know the range? Go, Brian. 0 to 3. So this one's a parentheses, though, because it doesn't quite get to 0. And then it does stop at 3, just like that. Is that what you meant? Yeah. Good job. So we just go case by case, through our notes today. So now you'll notice that m is equal to n in the directions. What they're saying there is that the degree of the numerator is the same as the degree of the denominator. Do you see that? So the degree of the numerator is 2, and the degree of the denominator is 2. Based on yesterday's lesson, you know that that horizontal asymptote is going to occur at the ratio of the leading coefficients, but we'll talk about that in a second. I go in order. So step 1, I try to find my x-intercepts by setting my numerator equal to 0. So the zeros of the numerator, I'm setting x squared minus 9 equal to 0. Now, you have a choice. You could factor that, or you could solve that by undoing. I would think most of you are probably factoring it. This does factor down to be a difference of 2 perfect squares. So it's x plus 3x minus 3. And then you set each of those pieces equal to 0. So you set x plus 3 equal to 0 and x minus 3 equal to 0. Subtract 3 from both sides, and then add 3 to both sides in the other equation using your addition property of equality and subtraction property of equality. You get your 2 zeros. So the zeros of the numerator are negative 3 and 3. Oops. Are negative 3 and positive 3. So we could say that negative 3 comma 0 is an intercept, and then 3 comma 0 is an intercept for this graph. Again, your table of values would verify this for you. When you go to throw it in your calculator, you go to the table. Right now at negative 3, you're going to have a 0, and at 3, you're going to have a 0 in the table. Okay, next up we have the zeros of the denominator. That's important because that tells us our vertical asymptotes. So the next step you would go ahead and take is you set your denominator equal to 0. So you could do a little bit of scratch work. I'm thinking most of you would factor that guy. So x squared minus 4 is actually x plus 2, x minus 2. Y'all did a nice job with that on your factoring quiz yesterday. That difference of 2 squares was hidden, I think, in one of your factoring problems. Using the zero product property, we can see that both positive and negative 2 end up being zeros of that particular function. So it's safe to say that x equals positive 2 is a vertical asymptote, and x equals negative 2 is a vertical asymptote. These are values that the denominator can't assume. For instance, if I take 2 and I plug it into the denominator, I get 2, square it, subtract 4. That's 0. You can't have 0 on the bottom of a fraction. And then if I took negative 2 and squared it, I'd get 4, and then 4 minus 4 ends up also giving you 0. So these are values that can't happen on our graph. We can't have x values at 2 or negative 2. The numerator and denominator do have the same degree. The degree of the numerator and the degree of the denominator is both 2. So our degrees are the same, which means your horizontal asymptote, real simple, is described as the ratio of the leading coefficients. Now, right now you're like, Mrs. Lucas, there's no coefficients there. What number is in front of x squared? Nick? 1. So to identify the ratio of the leading coefficients, it's just going to be 1 over 1. 1 over 1 is just 1. So our horizontal asymptote is just that y equals 1. So now I need to plot this stuff. Dirk, you looked very critically at it. Does that make sense? Okay. So now they kind of give you a nice little t-chart here. You can go to your table of values to, find the missing y values. You'll notice that they skipped out on negative 2 and 2 because those are our vertical asymptotes. So you can go ahead and draw those in. Oh, goodness. Okay, so we got x equals 2 and x equals negative 2. That oh goodness wasn't about the problem. Like I said, I'm not feeling well. So now, what we're going to go ahead and do is, we just plotted our vertical asymptotes. You could also plot your zeros, you know, -3, 0, and 3, 0. So we had some important information there, and then you want to put in your horizontal asymptote. We do have a horizontal asymptote now at 1. Because the degree of the numerator was the same as the degree of the denominator, and Nick pointed out for us that, hey, there's 1s hiding out in front of those x squareds. When you divide them out, you do get 1 over 1, which is 1. And now you're just going to take a minute to finish filling in your little t-chart there. So you go to your calculator, hit your y equals. Don't forget to quantify your numerator and your denominator. Zoom standard here. Kind of looks like a little smiley face right in the middle there because I'm in dot mode. So cute. Okay, so yeah, you're just going to take some time right now to basically generate this shape on your coordinate plane that you have in front of you. You could do that also by just grabbing some points off of your table. So a lot of things, you know, that we see here are sort of confirmed in what we found prior to starting the graphing part of the problem. For instance, I did see that I have an x-intercept at -3, 0. I do end up with a vertical asymptote at -2. I have another vertical asymptote at 2 because you can't divide, by 0 there. And then you have another intercept at 3, 0. The other neat part of this, just for fun, you can kind of see as you scroll out here. I said this is a little tip if you're ever in a jam and you really can't figure out the asymptote. As I scroll out right there, what am I getting really, really, really close to? Oh, it stopped. Natalie. 1, yeah. So you see this effect of the horizontal asymptote if you just scroll through your data a little bit. So we totally have that stuff. Okay, so right now you're going to take a second, fill in your t-chart, plot your curve. So ultimately I did grab some values off my t-chart there. And I plotted my curve. The last thing we need to talk about would be the domain and the range. There are actually 3 parts to the domain of this curve. 3 different chunks. Do you see them? Chunk number 1's over here. Chunk number 2's in the middle. Chunk number 3's to the right. That's your visual cue that you're going to have 3 parts to your domain. The domain of this graph starts at -∞. It's really, really close to -2. Takes a little break. And then we have the middle section. The middle section starts really close to -2 and finishes really close to +2. And that's in union with the third piece that starts at 2 and heads towards +∞ on the x-axis. So 3 different chunks to the domain. The range really only has 2 pieces. So as I look at the range right now, I see it comes up from -∞, gets really close to 1. Although it doesn't, the next piece doesn't start at 1, does it? What do you think? Well, yeah. Close bracket, open. Yeah, good. Or bracket. I meant to say bracket versus parentheses. I'm glad you knew. Yeah. So, yeah, this actually starts at that minimum value right there, that 2.25. And then it does head towards +∞ from that. So the range was a little bit trickier this time around. Is that what you were going to say, Nick? Good job. Questions about that one? Okay. Just in case, I am going to start the next example. There is nothing necessarily like this one on your homework where your m is greater than your n, but tomorrow's homework will have m greater than n. Okay, so if you take a look at the original problem, I'm going to, proceed through the normal protocol. I'm going to set the numerator equal to 0. I'm going to set the denominator equal to 0. But before I do all that, I just wanted to show you why this particular problem fits into this category. Notice the degree of the numerator is 2, but the degree of the denominator is 1. That means the degree of the numerator is greater than the degree of the denominator. So this actually isn't going to have, really any linear horizontal asymptote. So step 1, we find the zeros of our function. You set your numerator equal to 0. So I'm going to do x squared minus 2x minus 3 and set that equal to 0. Really, the only way to solve that is either the quadratic formula or factoring. Factoring is going to be way faster. Factors of -3 that make -2 when you add them together are -3, +1. So that's how the numerator factors. Factors to be x minus 3, x plus 1. And courtesy of the zero product property, if I set each of those pieces equal to 0, I could tell my intercepts are going to be at 3 and then at -1. So I can go ahead and plot those points. The 0 of the denominator, so that's the second thing you do. You set your denominator equal to 0. The 0 of the denominator is -2. That's the number x can't be, so we have a vertical asymptote at x equals -2. The degree of the denominator, or the numerator rather, is 2, but the degree of the denominator is 1, so there is no horizontal asymptote. So we found all of our basic pieces now. So we go ahead and make our t-chart and plot our curve. So if you take a look right now, you're going to go ahead and put this in your calculator. You're going to fill in your t-chart, and we're going to get your curve, okay?